All right, this is the second half of chapter 6, and we are starting today by talking about operations with radical expressions. This is going to be a lot of review from chapter 4, where we did a lot of review of how we worked with radical expressions. The difference being that this time, instead of just square roots, we're including third roots, fourth roots, fifth roots, and things like that. So we're going to talk about how to simplify, add, subtract, multiply, and divide radical expressions. Okay, so look for terms like rationalizing the denominator, which you should know what that means, like radical expressions, and conjugates, which you should also know. So the product property of radicals, you should remember this from chapter 4. But for any real numbers a and b, and an integer n is greater than 1, if I have the nth root of a product, that's the same as the product of the roots. So that's how we simplified things like the square root of 20. The square root of 20 is the square root of 4 times the square root of 5, right? And then I could say that was 2 square root of 5. So that's what the product property is telling us. And here they show you an example with cube roots. Since both of these are cube roots, I can multiply. The cube root of 3 times the cube root of 9 is the cube root of 27, which is 3. All right, so if we want to simplify this is a total review problem from chapter 4. The square root of 25 we know is 5. The square root of a to the 4th is a squared. And then the square root of b to the 9th, notice here they broke it up as b to the 8th times b, because b to the 8th is a perfect square. The square root of b to the 8th is b to the 4th. And so that leaves me with 5a squared b to the 4th times the square root of b. Okay, but let's look at what happens when I deal with a cube root, right? Remember, a square root, the square root of 25 is 5, because 5 times 5 twice is 25. Well, when I talk about cube roots, the cube root of 125 is 5, because 5 times 5 times 5 3 times is 125. Okay, so in this case, the cube root of 125 is 5. So basically with cube roots, I'm looking for sets of 3 equal factors that are multiplied together. So what they're doing here is they're saying, okay, well, 125 is 5 cubed, m to the 30th is m to the 10th cubed, p to the 20th, they're thinking of this as p to the 18th times p squared. Why? Because 18 is a multiple of 3. So 18 is p to the 6th cubed, because 6 times 3 is 18, and then I have this p squared left over. P squared is p times p. There's only 2 of them, and I'm trying to take cube roots, so I can't change anything about that, right? That has to stay under the cube root. So I use the product property of radicals, and I take the cube root of each thing. The cube root of 125, which is 5 cubed, is just 5. The cube root of m to the 30th is m to the 10th. The cube root of p to the 18th is p to the 6th, and then I'm left with the cube root of p squared. Be careful, don't forget to write the cube root if it's a cube root. If you don't write the index, it's not correct, because without the index, it looks like a square root. You have to keep that cube root in there if you're working with cube roots. All right, so it's your guys' turn. Try this one. Okay, the answer here is A, 4x squared y to the 5th times the square root of y. And for this one, your answer here is C. So notice this time we were working with fourth roots. The fourth root of 625 is 5. The fourth root of b to the 28th is b to the 7th. And we have to put this in absolute value because I took an even root, even index of an even power, but it came out odd. Then k to the 23rd, I split up into k to the 20th times k cubed, because 20 is a multiple of 4. So I know k to the 20th is k to the 5th to the 4th. That's why the fourth root of k to the 20th is k to the 5th. Then I'm left with the fourth root of k cubed. All right, let's remind ourselves about the quotient property. The quotient property says that if I have a fraction under a radical, I can take the radical of the numerator over the radical of the denominator. So for example, here I have the cube root of x to the 6 over 8. That's the cube root of x to the 6th over the cube root of 8. I can do them separately, and I get x squared over 2. All right, we're going to talk about rationalizing the denominator now, but you have to be a little careful because when our denominator is a square root, it was super easy, right? If you look at this example here, When it's a square root, I just had to multiply by the same thing because the square root of 3 times the square root of 3 is the square root of 9, which is 3. Right? A square root needs a set of 2, and in this way I give myself 2 3's to work with. But if I have an nth root, so a cube root or a fourth root or a fifth root, whatever, I have to make sure I fill in all of the missing factors. What do I mean by that? Let's look at this example. Here I have 5 over the cube root of 2, right? The cube root of 2, I'm missing 2 other 2's to make it a perfect cube, right? Because 8 is a perfect cube. I need 3 2's. So I can't just multiply by the cube root of 2. Notice here they multiplied by the cube root of 2 squared, because the cube root of 2 times the cube root of 2 squared gives me the cube root of 8, which is 2. So you have to be careful and fill in the missing factors. So let's take a look at this example. This is one like from chapter 4. So we use the quotient property, and then I simplify. So the square root of y to the 8th we know is y to the 4th. And then the square root of x to the 7th, notice the way they're breaking it up here, x to the 6th times x, right? So that's how they're breaking it up, because x to the 6th is a perfect square. And then that leaves me with y to the 4th over x cubed times the square root of x. But I'm not allowed to leave a square root in the denominator. So to rationalize it, since it's a square root, and it's one term, not a binomial, I just multiply by itself. So the square root of x times the square root of x is just x. X cubed times x is x to the 4th. That's where this comes from. And then my numerator is y to the 4th times the square root of x. But let's look at an example with a cube root, okay? So if I use my quotient property, I'm allowed to do the cube root of 2 over the cube root of 9x. So notice here they're rationalizing the denominator by multiplying by the cube root of 3x squared. Why? Because right now, under my cube root, I have 3 times 3 times x. In order to have a perfect cube, I need 3 3's and 3 x's. I have 2 3's, so here's my missing 3 I need to multiply by. And I have 1 x. Here are my missing 2 x's to multiply by. So what happens when I multiply those is that this becomes 27x cubed. And this is a perfect cube. The cube root of 27 is 3. The cube root of x cubed is x. And so that leaves me with the cube root of 6x squared. So in the numerator I just multiplied like normal over 3x. And now I've gotten rid of the radical in the denominator. Okay, you guys try this one. All right, your answer here is C. All right, and this is the work for that one. Okay, try this one. This is a cube root like the second example we looked at. Your answer here should be C. Here's the work for that. Notice I used the quotient property. The cube root of 8 is 2, so that's why I wrote a 2 here. What I'm multiplying by is in my denominator I have 1 3, and I need 2 more 3's to make it a perfect cube, so that's why I multiply by 9 under the cube root here. I have a y squared, and I'm just missing 1 y to make that a perfect cube. So I end up multiplying by the cube root of 9y, which gives me the cube root of 27y cubed, which is a perfect cube. Okay, simplifying radical expressions. We say that a radical expression is totally simplified when our index is as small as possible, and we'll see in future sections how to change that. The radicand contains no factors that are nth powers of an integer polynomial, so that means if it's a cube root, I can't have any perfect cube factors under the radical. I can't have fractions under the radicand, and no radicals in the denominator. So the rules are basically the same as they were with square roots. Actually, they're exactly the same. They're just applied to nth powers instead of just square roots. So when I multiply radicals, this is a throwback again to chapter 4, but this time we're using cube roots. I have to make sure they're both cube roots before I multiply, and they are. So I multiply what's outside the radical, which is just 5 times 1 in this case. And then under the radical, 100a squared times 10a. That gives me 5 times. If I were to write out what this would look like just as its full number, not factored, I would get 1000a cubed. But 1000 is 10 cubed, and a cubed is a cubed, obviously. So the cube root of 1000, or the cube root of 10 cubed, is 10. The cube root of a cubed is a, so I have 5 times 10 times a, which is 50a. All right, you guys try this one. Your answer here is B, 24A, and there's the work for how to get there. All right, adding and subtracting radicals. Again, you always just have to make sure that you only add and subtract, like radicals. But before I know if these are like radicals, I have to simplify. On your note guide, you should have a reminder of what like radical expressions are. So here we're going to simplify first. So I know that 45 is 9 times 5. I know that 80 is 16 times 5, and 20 is 4 times 5. So since these are square roots, I'm looking for perfect square factors of each of those numbers. So to simplify 3 square root of 45, I know the square root of 9 is 3. So I end up with 9 times the square root of 5. I'm going to back up here and just show you one at a time. So the square root of 3 is 3, so that comes out in front. So I'm left with 9 times the square root of 5. Here the square root of 16 is 4, so that comes and multiplies with this 5, so that's 20 square root of 5. And then here the square root of 4 is 2, so that 2 comes out. 2 times 4 is 8 times the square root of 5. Now these are all like radicals because they have the same radical and what's under the radical. So they're all square roots, and they're all specifically square roots of 5. And so, just like I would do with variables, 9 minus 20 plus 8, I add and subtract the coefficients since these are like terms. 9 minus 20 is negative 11 plus 8 is negative 3 times the square root of 5. That would be my final answer. All right, you guys try this one. The answer here is D, 8 square root of 3. And here's the work to get you there. Don't forget that even though the square root of 3 doesn't have a coefficient written, that there's a 1. So to get from 15 minus 8 is 7 plus 1 is 8 square root of 3. All right, multiplying radicals. This is review as well. Remember that when I have more than one term here and more than one term here, in this case I have a binomial times a binomial because they're separated with plus and minus, I have to FOIL. So 2 square root of 3 times 3, 2 square root of 3 times negative square root of 3, 3 square root of 5 times 3, and 3 square root of 5 times negative square root of 3. And here they're showing you each of those steps individually. So basically I end up with 6 square root of 3 minus 2 square root of 9 plus 9 square root of 5 minus 3 square root of 15. The square root of 9 is 3, so that's why I go from this to 6, negative 6. There's no other like radicals, so I just have to leave my answer like this. Okay, you guys try one. Your answer here is D, which you should have gotten just from foiling out your terms. Okay, this is just a reminder of using a conjugate to rationalize a denominator. So here they are giving us a geometry problem. In a square with side A, the ratio of a side to the difference between the diagonal and the side, so D minus A, is this fraction, A over A times the square root of 2 minus A. So we're going to rationalize and simplify this expression. So remember that when my denominator has a radical, but it's a binomial, I have to multiply by the conjugate, right? So my original one is A square root of 2 minus A. My conjugate is A square root of 2 plus A. I only change the sign in the middle. So I have to multiply numerator and denominator by that. I multiply, which they show you here. So I have to FOIL the denominator, distribute in the numerator. In the denominator, my middle two terms cancel out. That always happens when you multiply by a conjugate. So we end up here with 2a squared minus a squared, which is 1a squared. Oops, sorry, that went too fast probably. And then in the numerator, I have a squared times the square root of 2 plus a squared. What they're showing you here is that I'm factoring an a squared out of both the numerator and the denominator, and then that divides out, so that I'm just left with the square root of 2 plus 1 over 1, or just the square root of 2 plus 1. So if you can factor and cancel, or factor and simplify, you should do that. All right, that's the end of this video, and I will see you in class to practice simplifying more radicals.